Right. Today we will be discussing the basic concepts in geophysics, mainly on the properties of soil and rock that are relevant to geophysical surveys. First is the compression wave velocity, which is an important parameter in seismic refraction and in seismic reflection surveys. Compression wave velocity is the speed in which an elastic compression wave propagates through a medium. Now note that elastic means it is a non-permanent strain or a non-permanent deformation. For example, if you punch your classmate's face and his face recovers from the punch, okay, it's essentially an elastic deformation. On the other hand, if you end up seriously injuring your classmate and his face stays deformed after you punched him, then that is a non-elastic deformation. Okay, so it's important to distinguish elastic versus non-elastic because elastic ones are recoverable and they easily propagate through a medium, right? And by medium, I refer to solids and fluids for compression wave velocity. If you will remember, P wave velocities or compression wave velocities, they are compressional and they essentially can travel through air, water, and solids. Now, compression wave velocity is relatively easy to generate during surveys. As you can see in the photo, you can use a hammer or you can use explosives. Okay. And it's also important to note that the velocities of various rock types vary, and there's actually a big spread in the velocities per rock type. So it's a large range for every rock type, and as a consequence, it's very difficult or even impractical to determine the rock type based only upon the velocity. So in short, you can't rely on P-wave velocity alone to identify the rock type for a given site. And this is because there are various other factors aside from rock type that modify your P-wave velocity, and this include breaks or fractures. As you can see here, you can see the fractures here or the joints. All right, so if you're talking to a geologist, these are joints. If you are talking to an engineering geologist, these are discontinuities. And if you're talking to engineers, these are fractures. But nonetheless, these are breaks within the rock, and they disconnect your rock pieces. And as a result, they can slow down the overall propagation of your seismic waves. Another factor is the weathering. As you can see in this photo, you have your fresh here, you have a relatively fresh rock, and you have a relatively weathered rock, right? Note that weathering modifies your rock's properties. Okay? In simplistic terms, weathering turns your rock into soil, and that results in a drastic change in the elastic moduli of your rock material. Okay? It becomes less stiff, and as a result, you can have a much slower VP or propagation of seismic velocity in your weathered portion compared to your uh, fresh portion. Another factor is your saturation, right? Now note that dry rocks and dry soil, soil and rocks have their own pores or porosities, and in a dry state, right? In a dry state, rocks and soils contain air in their pore spaces. But in a fully saturated state, rocks and soils contain water in their pore spaces. Now you have to note that air and water have drastically different compression wave velocities. Okay? Compression wave velocity travels much faster in water compared to air. Approximately the velocity in air is around 300 meters per second. Okay, so that's the speed of sound, and that is also the speed of compression wave velocities in air. Okay, if you will remember, seismic velocities, or rather, are simply acoustic energy. Right? If you will note, seismic energy or seismic waves are just acoustic waves that are propagating or particularly propagating in earth materials. Right. Now going back, water has a significantly faster velocity, which is in the range of 1,400 meters per second. Okay. So now, if you have water in your pore spaces, you are definitely versus air. Okay. And seismic waves can travel faster in water. Therefore, saturation definitely can speed up the seismic velocity in your rock or soil. Okay, so in this case, in compression wave velocity, the presence of water actually makes your seismic waves go faster, right? And note that the primary property of your soil and rock that affects your seismic velocity is your stiffness. Okay, and seismic velocity increases exponentially with stiffness. So what is stiffness? Stiffness is it's sort of a brittleness of a measure of brittleness of your material. Okay, so it shows how fast your material can respond to an elastic deformation. So the faster that your material can respond to an elastic deformation, the stiffer it is. Okay? And another factor that affects compression wave velocity is the density. Technically, compression wave velocity decreases with density. All right, and and it's important to distinguish between stiffness and density. Okay, for example, diamond is a very stiff material but has a low density, while gold, which can easily deform and undergo permanent deformations, has a low stiffness but very high density. All right. Now going back to what I said before, rocks have a big spread in their compression wave velocities. And you can see in here, although it's quite small, so you can see in sedimentary rocks, for sandstone, for example, has a velocity range of 2,000 to 6,000 kilometers per second. So now note my question here is how many types of rocks here will you match if you have a velocity of 2,000 kilometers per second? So that's a lot. So rocks that have a velocity of 2,000 kilometers per second include sandstones, limestones, gypsum. Okay, all right. So at least you have three materials. If you will include soil, you also have your saturated sand and clay, glacial till, and so on. So you can see here that seismic velocity alone, all right, will not give you a clear answer of what rock type are you talking about, or what rock type do you have when you're just given the compression wave velocity. And this is the problem that applies to almost all of our almost all of geophysical methods. Okay, so it's actually important to have a clear understanding of the geology of the area even before you undergo or even before you do a geophysical survey, because otherwise you will be just guessing pointlessly. Okay, it you will have a very ambiguous answer if you have no idea of what materials are dealing to start with. Now, the next important parameter is the shear wave seismic velocity, right? So this is different from compression wave velocity as it involves obviously shear waves. And the important feature of shear wave velocity is that it cannot travel in fluids, mainly because fluids have no shear strength. Fluids have no response to shear stresses. Okay? I mean, you can slice air, you can slice water, but they don't really respond. They don't propagate the disturbance that you introduce to them if you introduce shear disturbance to them. All right. Now, what is shear wave seismic velocity? It is essentially a property that decreases with the rigidity of your material, right? Or in other words, shear modulus. Now, what is shear modulus? Shear modulus is the ability of your material to preserve its own shape, or the resistance of your material to changes in its shape. As you can see, as you can see in the in this figure here. Okay, you can see here that that a triangle, for example, is highly rigid. It can easily resist changes in its shape, while a square in here is quite susceptible to changes in shape, right? Now, shear wave velocity is also modified by your fractures, joints, faults, bedding, and also weathering. In soils and weak rocks, all right, it's also important to note that water, all right, affects soils and weak rocks in a different manner. Okay, saturation actually decreases the rigidity of your soils and weak rocks. Okay, if you're doing some soil mechanics or you're quite familiar with soil mechanics, you know that water can weaken your soil and weak rocks. Okay, it reduces their shear strengths, and in the same manner, introduction of water decreases the shear modulus of your soils and weak rocks, and in turn, this decreases the shear wave seismic velocity. Okay, so it's important to distinguish that, because in compression wave velocity, water actually increases compression wave velocity, but in shear wave velocity, for soils and weak rocks, you actually get a decrease in shear wave velocity. All right. Other factors, for example, is the relative density of your material. So relative density is different from density. Okay, relative density, I'm referring here to the compaction, or the degree of consolidation, or the degree of compaction of your material. So loose soils actually have low have a low shear wave velocity. Now, in order to generate a shear wave velocity, it's quite complicated. Okay, introducing a shear deformation to the ground. Okay, so what you have here in the photo, you have here a shear block, and you have here a hammer. So what the surveyor will do here is he will hit this shear block, all right, sideways, and the shear block will introduce shear to your ground, all right, and that will result in a shear disturbance. Okay. Now let's move on to another parameter or intrinsic property, which is density. All right. You will see later in our later discussions that density is a crucial feature in gravity surveys. All right. Density is important in gravity surveys in a sense that gravitational attraction, all right, increases when your mass increases and your distance between your two objects decrease. Okay? So gravitational force increases when you are close to an object. Okay? So when you're closer to Earth, you are actually feeling a stronger gravitational force. And when your mass or the Earth's mass is bigger, you are also experiencing a larger gravitational force. So what increases mass? Okay? Density. All right? When you have a bigger density, you have more mass per unit volume. Okay? So per volume, you get more gravitational force. Now let's talk about density again. So what modifies density is that are the following. So you have your type of material and as well as your mineralogy. And there are other factors that can change your density. For example, weathering. All right. I think we previously talked about the nickel laterites or deposits. So, for example, in rocks that contain magnetite, all right. So magnetite has a high density, which is in the range of 5,200 kilograms per cubic meter. So it is dense. Now, magnetite, right? Magnetite is actually quite susceptible to alteration. All right. So when you expose or you subject magnetite to heat and acidic conditions, you can yield clays. Okay, this can result in leaching out of your iron, and you will end up with clay materials. So I can't see where the clay here, but clay is approximately in the range of 2,000 kilograms per cubic meter. So you can see that weathering can drastically change the density of a material. Okay, and all right, but the value of gravity survey is okay in practice. All right, gravity survey is normally used in large scale or regional scale studies, particularly in mining and in petroleum exploration. And these explorations can easily exceed kilometers of surveys. And at that point, all right, weathering conditions can be quite negligible. And thus, all right, since weathering is quite an important factor that can change density, so once you start dealing with bigger or large scale surveys like kilometer scale surveys, okay, the weathering conditions okay, become less important, okay, and from there it becomes easier to distinguish types of soils and types of rocks, okay, particularly between sedimentary rocks, felsic rocks, and mafic rocks. Okay, so why? So sedimentary rocks, for example, might contain mostly lithic fragments and typically generally low density rocks, while mafic rocks, for example, will contain heavy minerals like magnetite, peridotite, and so on, which are much more dense. All right, the other property here, or the next property, is the magnetic susceptibility, which is important in magnetic surveys. Magnetic susceptibility here refers to the degree to which a substance may be magnetized. Technically speaking, almost e- almost all everyday objects can be magnetized as long as you introduce a sufficiently strong magnetic field. Okay, as long as you're introducing a magnetic field that is strong enough, you can magnetize almost any object except for a few ones, which we will be discussing later. So in here, this is actually a video of a frog that is being levitated by inducing magnetism within the frog. Okay, so they were introducing a very strong magnetic field within the rock, which made the frog magnetic, and as a consequence, it is reacting to to the other magnets in this chamber, which is causing the frog to levitate. Okay. Now, there are many factors that can affect the magnetic susceptibility or the magnetic response of a material, and one of them is the behavior of your dipoles. Dipoles are the atomic scale. These are the atomic scale miniature magnets that are present within a material. Okay, so we have dipoles, and depending typically on the mineralogy, okay, the dipoles in your material can react differently. Okay, for example, quartz has a negative magnetic susceptibility, and this means that when you subject quartz to a magnetic field, all right, quartz will align its magnetic dipoles in a way that it will counteract the external magnetic field. Okay, okay, so quartz hates magnetic fields. Okay, and if you it actually is able to produce a counter magnetic field to neutralize an external magnetic field. Now, the story is different when you are talking about magnetite. So magnetite can amplify magnetic fields. Okay, so even if you introduce a little magnetic field to magnetite, it can disproportionately amplify that external magnetic field. All right, these are the magnetic susceptibilities of different materials, and you have materials here that have negative magnetic susceptibilities like graphite, quartz, anhydrite, rock salt, marble, dolomite. Now note that dolomite can have positive magnetic susceptibility, mainly because dolomites can have impurities such as iron that actually modify its magnetic susceptibility. Another thing to note here that is that you have a non-linear change in magnetic susceptibilities here. Okay, so it can vary very, very widely in a sense that that pure magnetite can have a 1.5 or rather 15 million. Okay, no, not 15 million, but 15 trillion units of magnetic susceptibility. Okay. Now, our next property is resistivity, which is the ability of your material to resist the flow of an electrical current. And what affects resistivity is the presence of porosity, water, ions, and high temperatures. And resistivity is an inverse of conductivity. Okay. And for now, as early as now, I will tell you that resistivity surveys and electromagnetic surveys are quite similar, okay, in a sense that they measure electrical properties, okay. So electromagnetic surveys are much more closer to resistivity surveys because they both measure electrical properties, okay. So EM or electromagnetic surveys are quite different from magnetic surveys, okay, because magnetic surveys are concerned with magnetism, while electromagnetic surveys are more concerned with the electrical properties of your materials. Okay, now you have here a table of electrical resistivities of different materials. Okay, and there's not much to discuss here. All right, although it's quite important to note that clays are quite special in the world of electrical properties. Okay, I think I'll just discuss that later. But clays, all right, are slightly conductive. Okay, due to their clay mineral structure. Now, the next property is the electromagnetic wave velocity. Okay, so electromagnetic wave velocity is important, particularly in the penetrating radar method. Okay, so I think you've heard of that method before. GPR or penetrating radar is relatively one of the youngest methods in geophysics. Okay, and it's probably one of the most popular methods in geophysics. Okay, for many reasons, like for example, GPR can give you a real-time view of the underground. Okay, and it has a lot of applications, although it also has a lot of downsides, which we will be discussing later in this course. Okay, now going back, EM wave or electromagnetic wave is an oscillation or an alternation between electric and magnetic fields. As you can see here in this diagram, you have two oscillations. You have your electrical and magnetic oscillations, right? Okay, and I am a noob in physics, but at least I can tell you that this property of EM waves, right, makes it especially susceptible to materials which are conductive and have a high dielectric constant. Okay, so now let's discuss what is dielectric constant. Right, so the velocity of your EM wave depends on the dielectric constant of your material. Dielectric constant is the ability of your material to store a charge when it is subject to an electrical field. So, so it's sort of a material that can act as a battery. Okay, so any material that can store electric charge, okay, have a high dielectric constant, and there are many factors that affect your dielectric constant. Okay, the two main factors is the presence of conductive materials, and second is the presence of clay materials. Okay, and we will be discussing that later in this course. But those are the main factors that affect the dielectric constant of your materials. Right now, air has a dielectric constant of 1, and it can have one of the fastest propagation velocities of EM wave, while water has a very high dielectric constant of 81 and has a slower propagation velocity that is 1/10 to that compared to air. While metals have an infinite dielectric constant, okay, so metals just accept electric energy when they are subject to an electric field, and they have zero propagation velocity. Okay. Now, what happens when you have a material with a high dielectric constant is that they force, okay, dielectric constant forces your EM waves. All right. So if this is your EM wave, okay, so let's say this is your EM wave in air, which is quite fast. If you have an EM wave, for example, in water, what happens here is that high dielectric constants force your EM waves to have high frequencies and short wavelengths. Okay, so it sort of vibrates much faster. Okay, in in materials with high dielectric constants. Sorry. I think the correct statement here is that high dielectric constants uh, force the EM wave to have short wavelengths, okay, which can slow down their velocity. Okay, so you can imagine air is like a varsity sprinter, okay, that has a big stride, while your EM velocity in water is like a fast walker. Okay, so a fast walker is someone who can walk, uh, take a lot of steps, but each step is small, so that person can move quite slowly compared to a sprinter or a strider. All right, that concludes the lecture for this topic, and these are my references. Okay, so Parasnes and Telford. Okay, these are essentially the classics in geophysics. Okay, they are almost 10 to 20 years, even 10 to 30 years old, but I still find them relevant. Okay, they have the most detailed discussions of geophysical concepts. Okay, and another reference here is the Society of Exploration Geophysicists, or SEG website. Okay, so this is a very valuable website for finding definitions of geophysical terms. Okay, very helpful when you are studying a geophysical lecture or a geophysical material. Okay. All right, that concludes the lecture. Thanks for listening.